Hi, Ben.
For those on the line already, was anyone able to complete the part of the notebook and maybe to understand it down to here?
Okay, I think we can start. We can start now, and there is a recording. I think, who is recording? Is it Javi?
I'm recording.
Okay.
Yeah,
Sure. Yes, I think we can start now, and then we share the recording with those who are not here later. Yeah.
Okay, great. Can everyone see my screen?
Yeah, we do see your screen.
Yeah, so if anybody has any questions about yesterday's session, there was quite a bit of discussion about, probability distribution functions. It is a complex topic that takes some time to sink in, but you're welcome to write any more questions you have in our chat window and I can answer them as we go. So where we were yesterday, if you had either completed the, we set up the problem of this Bayesian bandits as a way of solving the class of problems. What object should you show to a user to improve some click-through rate, for example? Given that you don't know which of the objects or which of the creatives or which of the web pages that you could show the user would perform the best. And there was some discussion about, I showed how if we are lucky enough that we can reframe this question in terms of like a yes or no answer, or a this person clicked through successfully or they didn't click through successfully, sort of again like a yes or no answer, then we can reform this as a this looks like a Bernoulli distribution. And then we can very quickly determine update our information about the probability distribution functions. In this case, it was update our information about what's the probability that someone will click through from one page to the next page and then maybe make a sale. Given we can update this information given we have new information coming in about some past experience that we have, or some experience that we're gaining right now. And we were able to do this all with these beta functions. And I showed that the way that we can update our knowledge of these beta functions, and these beta functions describe the probability distribution functions for the click-through rate, is simply by adding any previous knowledge we have. So for our example, this was from our friend John, who'd already done a short experiment before, where he showed some creative to a particular to some users, and so he showed them to n users, or a number of trials was the number of times he showed the creative to different users, and the number of successes is what he's recorded. How many of those trials ended up with someone going through to the click through to the next page. And we can simply update our knowledge about the system, our knowledge about the probability of the click-through rate, using our previous knowledge, our prior knowledge that we got from John, and we update that with our new knowledge that we've just gleaned, or that we gleaned in our own experiment. And simply we add the number of trials together to get a total number of trials. We add the number of successes together from John and from us now to get a total number of successes. And then our beta function is described, our PDF is described nicely by this beta function with the parameters shown here: total number of successes, total number of trials. Okay, then I brought us to the point of saying, okay, let's have two creatives. A creative number one, where we have some information about the number of successes and the number of trials, and creative number two, where we have different number of trials and a different number of successes. And then we basically had to figure out, now if a new user comes to my website, given this information I have about these two creatives, which creative should I show them to maximize my potential click-through rate? And there was discussions about, should we use the peak positions of these distributions? And actually what we really should do is sample from both of these distributions and compare the sample, which is what we did down here. And the reason to do this is because these distributions are not delta functions. They're not very localized on the x-axis direction, which means we still have a lot of uncertainty about what is the right click-through rate here, or what is the best, what is the actual click-through rate for each of the creatives 1 and 2. And because we still have a lot of uncertainty, and this uncertainty is described by the width of the probability distribution function, so the width of these lines, then it still makes sense to sample from it. And even if there is very little uncertainty, so let's say we perfectly know the click-through rates, we can still use the same framework that we're building now in the future without any problems at all, without without affecting our results at all. So we can use this solution to this problem when we don't have much information, or we have very little information about which is the right creative. But even if we have lots of information about what's the right creative, we can still use this solution. We can still use the code we've written to solve the same problem, and it will work just perfectly. So you basically don't need to change anything. You just let the system evolve and let it run, and it will do the right thing for us. Okay, so then we came down to, this is the logic to say, we will randomly draw from these different beta functions from creative 1 and creative 2, and we will compare the random number that we drew, and if the random value we drew from creative 1 was from the PDF from creative 1 was larger than the random value we drew from the PDF from creative 2, then we'd show creative 1 to the user compared to creative 2. Otherwise, then we'd show creative 2 if the random value 2 was larger than random value from creative 1. And that's what we show here. Then I wanted to refresh our memory about the Bayesian Bandit algorithm. So this is the solution to this problem. And this is, we build our PDFs from our prior information. In this case, we use the beta functions to make this to make these PDFs and to encode our prior information. We draw a random sample from these PDFs for each of our different creatives. We compare, we identify what's the largest random sample that we drew, and which creatives does that belong to, and we would then show that creative to the user, to this particular user. And now we want to update this knowledge. Was this a success or was it a failure? Oh no, we record the knowledge. Was this a success? Did the user click through to the next page? Or was it a failure? Did they not click through? And then we update our probability distribution functions using this nice Bayesian formalism and these beta functions. And then we keep repeating this for as long as we have this creatives on this website, and we will actually get an optimal solution. I don't show that here, but we do get quickly an optimal solution. Okay, then I wanted us to encode all of this in this algorithm in this class, this Bayesian Bandit class. And maybe you, did this working? This should have worked. Oh yeah, I updated it. Were people able to get to this stage? Were they able to complete the code here, which I think we had? And were they able to pull the lever, or the pulling the lever is the same as querying our Bayesian Bandit algorithm to say what is the right creative to show. Were people able to get this far? Maybe you can either answer audibly or in the chat window. I don't hear or see anything written.
Yeah, I don't know if anyone has done. Maybe just they were. If anyone has done anything, just you can type it in the chat. But they were busy probably with other projects as well, so that's may.
Okay, understood.
Okay, so Stephanie said she did right there.
Great. Okay. Just give me 1 second. I just have to mute this call just a second.
Is anyone talking? What's happening?
He's gonna reconnect.
Okay.
In the meantime, anyone not following or struggling to follow, so that you can ask some questions we can answer on a chat. So we'll be able to to answer. I will answer in the chat if people are understanding something. Just type it. Go on, Ben.
Yeah. Okay. So thanks a lot. Sorry, I basically had a fire I had to put out with my with my job, and I just had to do some checks on some API endpoints we have. Okay.
Okay.
So.
But are you everything good now?
Yeah. Everything's fine.
Okay.
Oh, yeah. Basically. Okay. So. Right. Then let's go through this Bayesian Bandit class a bit slowly, just so people can follow what I'm trying to do. So we want to solve this problem of if we see these two or more creatives like this, how do we implement the Bayesian Bandit algorithm given that we have some different creatives to choose from? And how do we update this? So we basically want to implement this Bayesian Bandit algorithm in a nice class so that we can use this in our future code. And actually in like 10 minutes or so, I'd like to put this into a Docker container, describe what Docker is, and then actually have this as a working API that we can interact with. So the Bayesian Bandit algorithm, we'll build this as a class, and we'll first initialize the class, and we can either initialize it with an empty initial beta matrix, and this will actually be the beta matrix will hold the number of trials and the number of successes per creative, or per which we can call a different each creative we can call an item, to be more general, so that we can use this class more generally rather than just for creators of websites. So the beta matrix is just the number of trials and successes for each item. And item here, can you see my screen that I'm typing on? And each item here is, in this case, it's creative. It's more generic than creative. So
if
I
you can zoom out
my...
slightly, zoom in, sorry. If you can zoom in, that would be great. Yeah, that's great.
So the beta matrix is going to hold the number of trials and the number of successes for each item. So in this case, for each of the creatives. And what we're going to do is, if a particular item or a particular creative doesn't exist in our beta matrix, then we're going to include it. And this is like including a new creative in our analysis. So instead of having just 2 creatives, now we've got 3 or 4. And we just keep adding this, a new creative, and then we can add new information about this creative. So first of all, this add item method adds a new creative or a new item to our beta matrix. And we initialize that with some values if these values are not given. Then we have an update function. So this is an update method to our class. And this allows us for a particular item. So you can think of this for a particular creative. Let's call the creative number 1 and creative number 2. Those would be 2 different items. So for a particular item, let us update with a new number of successes and a new number of trials. This might just be, we might be updating in real time. So every time we have shown a creative to a user, we calculate, we measure, did they click through or not? In which case the number of trials would be 1, and the success would be either 1 or 0, depending if they click through or not. That's one way of interacting with this Bayesian Bandit. Or we could collect information on, say, a daily level. So we summarize for the creatives, we can summarize the total number of trials we had that day, might be 100, where we showed 100 creatives to 100 users. So we showed one creative number 1 to 100 different users. So the number of trials would be 1. The item would be creative number 1, and we calculate the number of successes we had. So the number of times that these users proceeded to the next web page. So we can update this either in batch or one at a time. And that's what these lines here do. First of all, they say, is the item, so the creative ID, if you will, is this in the list of items that we have in our beta in our Bayesian Bandit? If it's not, then add the item. If it already exists, then get the index of this of where this item sits in our matrix, in our beta matrix, and then append the number of successes and the number of trials minus the number of successes to our beta matrix values. This is the update function. Then we have a random draw function. And what this does is it takes the values that we are updating or that we're inserting into our beta matrix, And like we did before, where we did a random draw from the NumPy random beta distribution, so we do exactly the same thing here. But here we're actually working with arrays rather than individual, rather than with floats. And so this actually, this answer is an array. So this is an array of values of size, number of items in our Bayesian Bandit, and where the number of items is, in this case, the number of creatives that we have to show a particular website user. Now we have a pull lever method, and this basically goes back to this discussion about the Bayesian Bandit solution was a solution to the Bayesian Bandit algorithm. And remember, Bayesian Bandits was like a play on this slot machine. A bandit is actually a slot machine, and for a slot machine, you have a lever on the side that you pull when you play slot machines, if you're in Las Vegas. And so this pull lever is sort of like a play on this idea. And what this pull lever does is it selects random values from each of the different PDFs that we have. And we get that through this random beta draw. It identifies which is the best, which is the largest value from all these random values that we drew from each creative. And that actually returns the item which returns the item with the largest value. And so this is just some looking in. So we're basically using arrays and looking into arrays, which just means that this is very fast because we're working fully with arrays. And these lines of code here and here are actually very similar. It's sort of like an array version of what we were doing just here. Okay, so if you were able to implement this, and remember, if you weren't able to implement this, then in our Bayesian Bandit demo, then there's a hidden directory, and this master, the one that I'm showing now is this master notebook, and that is it's in this hidden directory, so you can actually take that and load it. So what we're doing is, first of all, we're setting up the Bayesian Bandit. And then we're going to populate the Bayesian Bandit with 2 different creatives and information about these creatives, so the number of successes and the number of trials. And what we can think is that our friend John ran 2 different creatives on his web page on a small experiment, creative number 1 and creative number 2, and he wants to give us this information about how many trials we had and how many successes we had. So we will update our Bayesian Bandit item by item, where item here is the creative ID, which is just here creative number 1 or creative number 2. And now what we can do is we can pull the lever. So imagine now we've got a new user is coming to our web page. We want to figure out what creative we should show them. So let's pull the lever, this Bayesian Bandit.pull lever, and this now tells us which creative we should show. So we are going to show this creative, this user creative number 1. This user we will show creative number 1. This user also number 1, and this user we're going to show creative number 2. We can simulate 5 different users like this. So now let us now add a new game into the mix, a new creative into the mix. So now we have a 3rd creative, and we also have a bit more information about the other creatives. Maybe we did our own our own little survey, and we've got some more results we want to add. And remember, it's very easy to add new information to constrain our problem, because we're always just these beta functions just require the addition of the number of trials and the number of successes. So it's very easy to add new data. So now, okay, we can do this. So let's say we have 3 create. Let me just reinitialize this, right? So let's reinitialize this again. We've got 3 creatives now. We pull the lever a number of times.
Ben?
Yep.
There is one question, a very good question from Stephanie, saying how many times should the BB pull lever in order to be able to choose a certain creative?
That's a great question.
Yeah.
And the answer is you keep pulling the lever every time, basically. Every time a new user comes to your web page, you pull the lever and then take the decision that the lever, show the creative that the pull lever suggests you show. And in time, the algorithm very quickly figures out which creative. So let's say there's a big difference in click-through rates from the different creatives. We don't know this before we start playing, before at the beginning, but the algorithm will very quickly figure out that one creative is a lot better than the other creative, and then it will always suggest, almost always suggest showing only the best creative. So the solution to this problem and pulling the arm, you should always do every time a new user comes to your web page, and we will very quickly get to an optimal solution. So basically, you should always pull a lever every time a new.
So if I can ask, just because that's a really great question for others to reflect, what does that mean? Like, so Ben said that, and how would you understand that in a different context? So from probably the probability distribution that you have seen earlier. So what would be that? What would that mean? Like Ben said, that at some point the algorithm will just figure out that, and then will always show one. What does that mean? Can anyone answer with respect to these distributions? Yes, it's a good attempt. Yeah, probability of one of the creative will be close to 0, but not necessarily. Okay, so now Ben is showing you a hint.
Right, so it's not necessary that one creative will have a click-through rate that's close to 0. They might be both quite good.
Yeah.
One might be, they are what they are. We don't know what they are. But we learn what they are. And so if you're in a setting like this, where we have we've got two creatives, and one was very successful. We had one, we showed this creative 1,000 times, and we had 750 click-throughs, which means it's like 75% click-through rate, compared to this creative, number 1, where we showed it 200 times and we only had 80 click-throughs or 90 click-throughs. Then we see that these 2 PDFs are very disjoint from each other. And this means that we will almost always recommend showing creative 2 to a new user compared to creative 1. And as we get more and more information, and as we continue to, what does it mean to show only from the yellow distribution? What it means is that we will pull the lever, and the suggested creative that we show will say creative number 2. It would say, just keep showing creative number 2. So let's see this in action, shall we? So let's do this for 50 times. And what we see is that we had these two probability distribution functions, two different creatives. One creative appears to be working a lot better than the other creative. So let's see, do we always show creative number 2 to these 50 new users who are entering our site? And you see that we're showing creative number 2, we're showing creative number 2, we're showing creative number 2. The algorithm has very quickly learned that just creative number 2 is better than creative number 1. Therefore, it's in these 50 examples, it's shown them, I think, every time. Okay. Does that answer your question?
Yep. Go.
Great.
Yep.
Okay. So now let's take a step back a minute, and I want to play a game. So up to now, we've been basically building these Bayesian bandits and pulling the levers. But what I'd like us to do is to pretend that I want to split the universe into two, right? And in one universe, I want us to have a very boring algorithm that shows each of these creatives, creative 1, 2, and 3, it's going to show them each 10,000 times to 10,000 different users. And we're going to calculate the actual click-through rates based that we've shown this on to maybe say 100,000 users. So we show each creative 100,000 times to 100,000 different users. Maybe we waste a lot of money by doing this, but in this universe we don't care. And through that, we will actually be able to calculate the correct or the actual click-through rate of each of these creatives. So I'm showing them here to be creative number 1 has got an actual click-through rate of 0.7, creative number 2, 0.3, and creative number 3, 0.5. So this is in our separated universe. This is the actual truth. Now we can let's use this information in our let's come back to our universe now, where we don't know, we didn't waste all of this money and all of this time, and let's see if our algorithm quickly learns which of these 3 creatives is the best one to show based on an update. So we pull the lever, we determine, was this a success or a failure in our universe, and we update based on this information. Now, to play this little simulation, I actually need to know, was this, if I show a particular creative to a user, will it be a success or not? So I actually need to take the information from our parallel universe where we've already calculated this, and that's what we're doing here in this random choice. We're saying this was a success with value with the value of that's shown here. So for creative number 1, for the item, we pull the lever and we get a creative value. So let me print item. This is the creative. Exactly, that's what we want to do. So this is a simulation we're setting up to show how brilliant this Bayesian Bandit algorithm is. Okay. In the real world, we won't know this. This success or failure information will actually come from us watching the data streams in real time and figuring out, did a user go to click through to the next web page or did they not? But here we can make a simulation, and we're going to use this parallel universe to help us do that. So we're going to choose, for this particular creative, we're going to choose the value 1, a success, with a probability based on information from our parallel universe that, of course, in the real world we won't have, but we're in this simulation now. Then we update our algorithm based on this knowledge of this success or failure. And then let's see what happens, shall we? So we've got 3, at the beginning we had these 3 creatives, and you saw that if we pull the lever 50 times, we get a range of creatives, 1 and 3, sometimes creative 2, but basically all these 3 creatives are about the same. Now let's pull the lever and see what happens. So the best creative that we could be showing them is creative 1, right? Our algorithm doesn't know that, but we should learn that. And let's see what happens. So at the beginning, so every time we pull the lever, we show this creative and we figure out if it was a success or failure, and then we update based on this information. What you see is very, very quickly, our algorithm has figured out that creative number 1, now it's actually just, oh yeah, okay, let me just restart that here. Our algorithm very quickly figures out that creative number 1 here actually looks too good. I must have made a mistake. That's even too good even for this word. Start the Bayesian Bandit, update it with this information, pull the lever a few times.
Yeah. Ben, can you make it instead of 0.7, make it smaller?
So I can, but let me do that in a minute.
Sure. No, I'm just, if it's too good, that's what I'm saying.
Exactly. So we got this Bayesian Bandit here. We're updating it with this information. Let's actually start with no information about the games whatsoever. So our prior, we don't know which is the best creative. So that's our starting point. Now it's stuck on 1. No, something's gone wrong. What am I doing? I've made a mistake somewhere. Here.
No, in the printing.
Delete the Bayesian Bandit. I reinitialize the Bayesian Bandit. I set everything to 0. I've updated it based on basically nothing. And it's only giving me once. What's going on? Carol, restart and clear output.
Exactly.
I wonder if I've added a bug somewhere. I must have done. Wait. Okay. So here we are. The creative is showing us. The suggestion is, sometimes show creative 1, sometimes show creative 3. It doesn't know. And now we're going to play this simulation and see what the result is. So at the beginning, it's like, oh, maybe show creative 2, but this wasn't a success. Then for show creative 3, this was a success. So probably creative 3 is better than creative 2, but let's keep going. And at some point, we should start showing creative 1 there. We should see that gives us that was successful. And then as we play the game, we should see more and more of these creative 1s appearing as the one we should show, as the algorithm learns that this is actually a far better creative. So let's play it again. And okay, now we've played it again and we've seen that. So now after 200 pulls, we very quickly figure out that creative number 1 actually has a better click-through rate, and therefore we should show it to our users than the other creatives. So this is us seeing in real time that the Bayesian Bandit algorithm is working. Okay, are there any questions about this before I move on to the Docker container part?
I think for the sake of time, just let's move there.
Okay. Docker containers are they're a brilliant way. So have you ever been given a new laptop or a new computer, or have you ever had to work on a different computer to the one you're currently working on? The answer is probably yes. Did you ever have problems installing like packages or Python or machine learning codes, or getting your trained machine learning model? Did you ever have problems setting that up from one system you're working on compared to a system where you maybe want to run or another system that you had? If the answer to this is yes, then you've encountered the perfect opportunity, or the actual reason why Docker was born. Docker was born so that you can encapsulate everything about your system think of this as like a little microcosm universe that only interacts with the outside world in some specified ways. And now in your little micro universe, you define what is the operating system. Is this a Linux environment or a Windows environment? You define exactly what version of Python you want. Is this Python 3.7.1 or this 3.6 or 2.7? You define everything about your little microcosm universe so that it exists, so that it works. Now you can take this using this thing called a Docker image, and an image is like it's a copy of your of this micro universe. You put this image on any computer anywhere on the planet, and the system, this little micro universe, will run the same absolutely everywhere that you put it, which means you never have to worry about configuration or operating system changes or anything, because all you're doing is taking this image of this little microcosm universe, putting it somewhere else, and it will work exactly the same way as it works on your local machine. So if you're if you want to deploy a machine learning model, for example, then it's great to package everything up in terms of this little microcosm universe, a little Docker container. Then we can put this Docker container on, you can give it to your friend, he can run it on his computer, you can put it on AWS or on Azure or on cloud or Google Cloud or any web or any other computer or any cloud service, and the system will run exactly as you expect it to run without any headaches. So Docker is brilliant for compartmentalizing your code, your configuration, and even your machine learning models, putting it somewhere else and having it run. Now, a great way of interacting with this micro universe is through API calls. So basically, what we build is our microcosm universe will have a little web server, and it will be listening to API calls, to HTTP calls to this micro universe, and then it will do something based on this on this API call. So let's see this in action. What we do is first we have a Dockerfile, and now if you go to my Bayesian Bandits directory, we actually have a web app directory, and in it is a Dockerfile. This Dockerfile says now you can copy this and you can run this code locally, and everything will work perfectly. Yeah. So what do we do in this Dockerfile? This Dockerfile describes how we build our microcosm universe and our system and all the configuration that we want. So we say, okay, I want it to be Python 3. You can specify, like, you should Google how to change this to be a different operating system. You want it to be Windows operating system running Python 2.7. So basically, there's lots of changes you can make here about what the base operating system is, but we can change that here. Then we run some commands like update the system. We want Python to be upgraded. We want Python pip to be upgraded. We then want to install a requirements.txt file. And so this is all commands that I'm giving to our micro universe so that it can build itself wherever it goes. And for our purpose, I actually have a requirements file. And if you're used to installing things from a requirements file from Python pip, then all we're doing is we're going to have NumPy installed. We're going to install Flask, which is a web server for Python. So install our requirements, set up a working directory where we're actually going to work with inside this micro universe, copy some stuff that's in this lib directory in this app file, and then start the this command, which runs at the end of the Docker file, starts the web service and starts listening on our starts our micro universe listening to the outside world for some requests. Now let's have a look at this app file, app.py. What we're really doing is we're building a Flask server. So this is just a web server using Flask, which is a nice Python web server. We're going to listen on a particular port number, and this port's going to be 8080. And then we're going to have we're going to set some API endpoints. And what this is different. We're going to have set up different API endpoints which can talk to our our Docker container or our micro universe, and based on the API endpoint, then we're going to take different action. So the first action we're going to take is just to check, is the system working? And that will just print hello world to the screen. The second action we're going to take is we're going to have a Bayesian Bandit running, and we're going to update the Bandit, a lot like our update function that we had here. And we're going to pull the lever exactly like this function here. And these are going to be HTML API endpoints that provide this action. And then within this API endpoint, we have just a set of code to perform the task that we want. Down here, we just have some more code that just will allow the app to run, to build itself and to run. Now, what I've done is in a lib directory. So we set the Bayesian Bandit problem up, and I've built in the lib directory. There's a Bayesian Bandit file, and I've actually just copy pasted the class that we wrote here. I've copy pasted this and put this into this library file. So let's run our little micro universe. I hope that you've all installed Docker, because to run our micro universe, we need Docker running, and it doesn't matter which operating system your Docker's running on, it's always going to build a little micro universe in exactly the same way, and then we can interact with it. So I've actually written a helper function called build.sh, and this just runs two commands, which one is to build the Docker container, which is make build the little Cosm universe, the Docker image, and then run it, and then run it. So these are just two commands that we're gonna run from the command line. We're in the web app directory. You see my build.sh file, and we're just gonna run this. And what we see is that for you, it might take some time to, basically you need to download some packages from the internet and construct this micro universe. It might take some 5 or 10 minutes depending on your internet connection. But the end result is that you will have a screen that looks like this, where stuff is downloading and installing and running. And then there's a notice here saying running on this HTTP endpoint. And this means our microservice, our Docker container, our Docker image is built, our micro universe is built, and it's listening, the web service is listening on this HTML endpoint for requests. So let's see if this works. Indeed, if we go to this /API endpoint, our result is hello world. And this just shows us that our micro universe is working as expected. Is anybody able to complete the step up to now and to run the Docker container? and to interact with this web page like this.
I did, but let's see if
Okay,
someone else.
I've not heard anything, so maybe that's a no.
Yeah.
Don't worry. You can. I mean, I've written all the code in our our GitHub repo. Just make sure you download it and run the commands that I've run here. This bash this build command. Maybe I'll put that as an okay, yeah. So now we have our micro universe running. Let's actually test it from within our the Jupyter Notebook. And so what's super nice is we can actually use the Jupyter Notebook as a sort of like an API endpoint testing system, if you will. You can also use Postman, or you can use the command line to do this, like wget even, or curl. There are many ways of talking to different API endpoints. And I just want to show you one way of doing this with Jupyter Notebooks. And we're going to talk exactly to the URL that's suggested here. Okay, let me change this. The URL is suggested here. And we are going to just interact with the code a lot like we were interacting with the code during this above this in the Jupyter Notebook. So we're going to have to put some creatives. We're going to post this information, or this JSON file, or this JSON list, if you will. We're going to post this to our update Bandit API endpoint, and then and what we see is we get a response that says 2 records have been appended. If we had more than 1 creative, so if we had 3 creatives, then we would see so creative number 3. 3, let's do this. See that ANCA. You see that 3 records were appended, because we had now 3 creatives. And then I've actually just I've also got a dump beta matrix parameters API endpoint, and all that does is actually show the number for each creative, shows the number of successes and the number of failures that we have and the number of trials. Note that this is always cumulative. So as I've run this twice, so then we've updated information about creative 1 and 2 twice, and creative 3 has only been updated once. So this should be 1 and 1, and that's what we see here. So now let's interact with our this micro universe. Let us pull the lever a few times, and pull the lever and update the bandit based on again this. So again we're in a little simulation, and we're using information from this parallel universe where we had infinite money and we didn't care about costs and things. So we ran a lot. We showed very many creatives to very many users, and we got the true click-through rate, if you will. And what we see is a lot like what we had before. We're interacting, we're updating the information of was this a success or was it a failure? And then this actually updates our Bayesian bandits. And so at some point, the algorithm always suggests showing creative number 1 compared to the other creatives. And we can see what we've actually learned here is that creative number 1 has been updated very many times. Creative number 3 was actually shown to be quite poor, and so we didn't update it many times. Number of trials is 17. Number of trials is 19. Number of trials here is 91. which basically showed that we very quickly learned that creative number 1 is a lot better than the other creatives. So there's a lot to digest here. Basically, what we've done is we've used Docker containers to build a micro universe that hosts a website or a web interface, and we're using Python Flask as our web interface to talk to the code base that we built. And for this purpose, we've built a Bayesian Bandit code base. But you might want to build, of course, you can build other machine learning code bases. Okay. So now to summarize and to conclude, I hope I've showed you how great the Bayesian Bandit algorithm is. Actually, Yabi and I have seen this in real-world examples working brilliantly, and it works brilliantly. Do try to use it in your workflow. You can tackle a range of very interesting problems with it. I've given you a very quick introduction to Docker, Flask, and APIs. They can really make your life a lot more stable and a lot better. Do take time to look into these and learn about them and implement the code that I've written. Everything should just work off the shelf. And then, yeah, there's been lots of interest about internship opportunities at Carl Zeiss. Ping me if you're interested. I am talking to my bosses about this in the coming days. I will basically get a requirements list, and then I can send that out to you. We might have a challenge to give you, and then we can see how this works. But yeah, ping me if you're interested, and I promise to get back to you within by the end of by next week, as I talk to my boss this week.
Yeah, definitely.
That's it.
Ben,
yeah,
thank you so much, and we definitely will get into this. We'll discuss, and in particular, one of the things that you mentioned, which is also going to be useful for the internship, would be like the machine learning failure. We are looking some kind of challenge on that, and if we could design something like that, or what you have been working, that would be great. So I mean, we'll just keep in contact. But really, thank you so much. It was really a lot of stuff. I think people were busy with the challenges of this week. That's why probably they interacted less, but definitely would like to see that again with another challenge, which has its own week. That would be fantastic.
Great.
Okay, so
yeah,
Anastasia has a question.
I have a question. Is successes and trials only? Can we use Bayesian Bandits with more than 2 features as inputs? So this is a good question, and what you can think of is so the Bayesian Bandit algorithm solves this Bernoulli trial type of problem, and this is drawn from sets of true positives or yes nos or 0-1 answers and questions. However, what we might care about is saying, given that I know the web browser of this particular user, now what creative should I show them? And so that you can think of that as an additional feature that you can feed into the algorithm. And then what you can basically do is you can split it and say, rather than having an item, which we've been calling it maybe creative up to now, you can call an item creative plus operating system or creative plus web browser. And then you can quickly learn which is the best creative to show to a user based on their web browser. And so there's various ways that you can sort of you can use these features, additional features in this analysis.
Yeah.
And there are other extensions to this, but sadly I don't have time to go through. Okay.
Can we integrate?
Right, and I have to go. Thanks everyone a lot for your attention. And
thanks, Ben.
Taking the time to meet with me. And you can ping me from questions on Slack, and I will check from time to time and get back to you.
Fantastic.
Thanks, everyone.
Great. Thanks. Bye. So Stephanie, just for